Welcome, ladies and gentlemen, to the public forum of the group exhibit Hydrogen and Fuel Cells and Batteries here on Hanover Fair 2014. We have a very nice program here, every 20 minutes another topic. And now we're discussing R&D challenges and opportunities for advanced electrolysis technology. Very happy to have with me here on stage the manager of Department Electrochemical Energy Technology from the Deutsches Zentrum für Luft und Raumfahrt e.V. DLR, Institut für Technische Thermodynamik, Dr. Johannes Arnold. There he comes. Dr. Arnold, it's a pleasure having you here. Please have a seat. So, and whenever you have the feeling you would like to ask a question or you would like to comment, so give me a sign. I'll be with the microphone right with you. Dr. Arnold, we're talking about R&D challenges and opportunities for advanced electrolysis technology. What is advanced electrolysis technology?
Yeah, well, this is a good question. Electrolysis itself is an old technology. It exists for now more than 200 years. And already in the beginning of the 20th century, there already existed 400 or more facilities that are using electrolysis technology. But
we always say it's a new technology, upcoming technology, but it's 200 years old, obviously.
Yeah, but then 2 world wars later and a lot of development, and it was forgotten, electrolysis, and it was not so important. And then in the beginning of the 1970s, with the first oil crisis, situation changes, because now it was seen, okay, oil is not running forever. We need some new solutions. And then they detected or they discovered again electrolysis, and at that time it was the beginning of this, let's say, advanced electrolysis. This means it was alkaline electrolysis of water, but by using renewable energies. And at that time it was in the beginning solar technology.
That was very interesting, because I can remember 20 years ago when we started this group exhibit, everybody was talking about it. High Solar, it was called. It was a project from DLR, and it was with Saudi Arabia. So they believe they run out of oil and then they need something new, which is hydrogen.
Probably they wanted to be sure that if oil will be disappear or will not exist any longer, then they will have alternatives. And at that time, really, there was a project of DLR together with Saudi Arabia. And the main goal at that time was to realize electrolyzers and with special features. And one special feature was that if the sun is not shining any longer, that the electrolysis is still running. And it happened. We were successful at that time. It was possible to get an electrolyzer here in Germany of 10 kilowatts that is running during the day, and in the night it will not be, you don't have to put any protection currents to run it. Also, it could run without any protection current, and this was a big success. And in Saudi Arabia we were also able to produce an electrolyzer of up to 350 kilowatt.
And these electrolyzers were alkaline based.
These were alkaline based electrolyzers.
Okay, and so that I understand it, you always need some current before the electrolyzer starts working, and you managed it there in Saudi Arabia to produce electrolyzers that didn't need any current, even at night?
Even in Germany. We were also, this current is not for starting, but when there is no sun, when there is no energy, that there is no oxidation in the electrolyzer. To prevent this oxidation, normally you need this. But in this project we put some special coatings on top of these surfaces, and with these coatings it was possible that there is no current, protection current needed to do this.
I see. So you were very far in these days. This High Solar project was from 85 till 95.
Exactly.
And well, why didn't you go on with that? Well, you could have just gone on and be today with electrolyzers that don't even sun anymore. Don't even need sun anymore.
As usual in life, you want to continue, but there are other forces that stop you. In this case, the oil price was not too high enough. This was one side, and the other side was that politicians said, okay, this is not any interesting any longer for us. Let's stop it. Founding stopped, and so we have to stop our work. And we are starting to concentrate more on this new topic at that time. This is fuel cells.
The fuel cells. But we're coming back to electrolyzers. Everything is coming back in history, as we all know. Now to electrolyzers. Why is it so important today?
Because this German Energiewende, or this Energiewende at all, happened now 2-3 years ago. And with this change, electrolysis becomes interesting again. Why? Electrolysis can be very efficient if you have cheap current, if you have cheap resources. And with this German Energiewende, you probably you suddenly have wind, you have solar technology again, and the problem is these are fluctuating energy resources, and this means what to do when you need energy, but there is no energy available, probably in the night. And there are scenarios also from the German from Deutsches Zentrum for Luft and Raumfahrt, where it is shown that probably in the year 2050 we will have an excess energy of maximum of 40 terawatt hours, and on the other hand, there are in the worst case we need 40 to 50 terawatt hours when there is no energy available. And for this, electrolysis would be a really strong tool, because you can use it for storing the surplus energy you have probably during the day.
What we need is base loadable energy, and what we have is volatile energy. So when the wind is blowing, the sun is shining, we have the energy. If not, we need old coal plants are running. So we have the funny situation in Germany that we have more renewables in the grid than ever, but also more CO2 than ever, which is funny, isn't it? It's a paradox.
This is quite sure. There are two possibilities when you have these fluctuating resources. For sure, you can say I don't need any storage. I don't want it. So let's build more wind wheels that are necessary, that can compensate with this deficiency of energy. So somewhere in Germany there will be wind blowing all the time.
But that's costly, I think.
This is very costly, and I'm really not sure if it's really the truth. But by the way, there is another project. It's called Desertec project, and with this Desertec project, this is a combination of Northern Europe, or Europe with Northern Africa, and combining all kind of sources: solar technology, photovoltaics, wind, water. And in this case, it's possible that, or very likely, that there is some energy everywhere. But within Germany, I guess Germany is too small that you can say, okay, there will be wind all the time.
But Desertec is almost dead, isn't it? Because the energy will never come to Germany, even if they install it there. They all need it in Africa.
I doubt it. I guess there's enough energy. So I don't know if Desertec is really dead, but
okay, we will see.
We will see, exactly.
But we have to come to the fact that we will have to pay a price for energy storage. If we have volatile energy sources, we also need energy storage possibilities, and that costs a price.
Absolutely. And I think this is something one has to, politicians and also scientists and technicians should explain to the population that the price will be higher, because now we have to add also storing to not also consuming but also storing. In the past, nature did it for us, storing. But now we have to store by ourselves, and then this increases the cost. Okay, the increase should not be too high, but it will increase the cost.
So we can store it by converting the surplus energy from the grid into hydrogen via electrolysis, and store it, let's say, in the gas grid or in gas caverns or wherever. Yep. What will be the price then for this energy? Could you tell us?
There are different scenarios. As far as I know at the moment, they are for today the calculations are 25 cents per kilowatt hour. But this is really too high, and the goals or the aims that they will try to reach is probably 10 cents per kilowatt hour in the future.
we have to reach that goal, yeah. But
This
therefore, we have to do a lot of R&D, probably.
Absolutely.
Okay.
This depends if we are able to reduce the cost, the commercial cost of the electrolyzers itself, of the facilities, and of the process itself. And this is one of the goals that we from DLR, but also from the Helmholtz Association, want to do now in the next 5 years. Just this week, there was a program from the Helmholtz Association that is putting 62 million euros per year in development, in research of storing of energy. Storing not only by hydrogen, but also storing of heat, storing by thermal heat, or storing by pumping station water, pumping stations.
There are always different opportunities, you know, and you prefer electrolyzers because you are doing R&D on that. I can understand that, but why not using natural gas? Let's have a look at the United States. They have the shale gas boom. We might have a shale gas boom as well in Europe or in near Asia, and use a lot of natural gas and reach the CO2 targets like the United States do already.
Yeah, you're right. For sure, natural gas have many advantages. One is a lot of natural gas is available, and also the extraction, the distribution, the storing is available, and will also be available for the next 10, 20, 30 years. This is not a problem. But on the other hand, especially the extracting here in Germany will be difficult. I'm not sure if it will be politically and technically possible to do fracking in Germany. And this means if we are not able to do it here, we have to find other solutions. And
or we import it from Russia, but that's also not a good idea.
Or we are depending from other states, other countries. This may work, but if it's going wrong, then we have a big problem.
So steam reforming is not an option for you. We could also do steam reforming, have a lot of hydrogen then from that.
Yeah, for steam reforming is also an alternative. But I think hydrogen has all the other big advantages because you can convert it probably to synthetic hydrocarbons. And these synthetic hydrocarbons in gaseous form or in liquid form can be used for other things. And this you can't do with steam reforming. So hydrogen has some advantages.
Okay, let's come back to electrolyzers. We have been quite a lot of discussions here in the forum about PEM electrolyzers, alkaline electrolyzers. In general, you could say alkaline is cheaper now, PEM is more efficient now, isn't it?
This is the common opinion, and it's probably true. The alkaline electrolysis is very mature at the moment. The same holds also true for PEM electrolyzers. Also, they are very efficient for small facilities. But if you increase the PEM electrolyzers, you increase the problems, and these problems have to be solved. Alkaline needs also some development, but I think there is another kind of electrolysis, and this is a high temperature electrolysis, the SOE. And
solid oxide electrolyzers. We all know solid oxide fuel cells, and since, well, a fuel cell is like a reverse system of electrolyzer, you could also do solid oxide electrolyzing. How does that work?
As you said, it's mainly the reversal of a SOFC. But you have, with the SOE, you have a big advantage comparing to the SOFC. If you produce heat or too much heat with the SOFC, this is a problem for you. In the SOE, more heat can be used very efficiently and very in a good way, because it reduces the power, the electrical power you need to run a SOE system.
I know there is a lot of industrial heat in Germany and other European countries, which is not needed, which is just blown into the air. Yep. You could use that heat, couldn't you?
Absolutely, absolutely. And this is one of the goals, to use this heat, this surplus or this excess heat in SOE technology.
You need temperatures like 900 degrees or something like that in SOE?
Let's say between 600 and 1,000 degrees.
600 and 1,000 degrees. Yeah. So, and you always have to feed the system with the heat. It doesn't produce the
Ab-
heat itself when it's
Absolutely.
electrolyzes.
And the more heat you can, at higher temperatures, you can give in, the less electrical energy you need for this conversion of water to hydrogen and oxygen.
But the same is the system is the same. You put water in, H2O, and get hydrogen out and oxygen out.
Exactly.
But you also can add some CO2, can't you?
This is also a big advantage or possibility you can see with SOE, that you can make this kind of, this is called co-electrolysis. This means electrolysis from water plus electrolysis of CO2. Because if you are able to do this, on one hand you are getting synthetic hydrocarbons again, and on the other hand you are able to reduce the greenhouse gases when you are able to do this.
So I was just talking about the industrial heat you could use. Some of this industrial heat comes from burners, or they produce CO2 and they don't know where to put it. They also blow it into the air. They could use it in the SOE
Exactly.
and make methane from it.
For example, a lot for sure. This is not, we can say, okay, you can do this today, but I think this is the content of research and development that has to be done within the next few years. And if we are successful in doing this, I think this is a really nice goal to get to this goal.
I think that's very exciting to hear. You can use two sources of, well, energy and a product that nobody wants, like CO2, to produce something that is really needed, like hydrogen and methane.
Yeah.
Very good. So you're working on that?
We are working on this. Next step is also, for sure, this would be in the, let's say, in the gaseous way. If you are able to run these electrolyzers in a pressurized mode with higher pressures, you can get it in get the results in liquid form. And this is also a very nice goal that we
liquid syn fuel, you would say then.
Absolutely.
Oh, great.
Absolutely.
Very good. But I could imagine such a high temperature electrolyzer needs material that can bear these high temperatures of 600 to 1000 degrees. That's not easy to find the right materials, is it?
Is correct, but on the other hand, we have the experience of now many years of research on SOFCs. And SOFCs at the moment have the same materials. It's not clear if the materials you are using today for SOFCs are also the optimized materials for SOECs. But it's a starting point. You can start with these materials and then you can see what's going on, probably to get better or more efficient results.
Are there any questions from your side? If there are, please give me a sign and I'll be with the microphone right with you, and so you can discuss well, these for me quite astonishing and new impressions about SOE, which is quite amazing what the possibilities could be. Yeah. But you don't put all your money on one card. You still go on with PEM electrolyzers. Exactly. What's to be done there?
PEM electrolyzers are or can be very efficient, and I said it before, if you have really small facilities, they are really very efficient. And also the purity of the hydrogen you are getting out of this is very high. But the problem starts when you are increasing these PEM electrolyzers to bigger sizes, because then the membranes, for example, get more brittle, and also the flow inside, the gas flow or the water flow inside has to be handled different. And for all these things you have to find solutions. At the moment it's well known for small facilities, but now the next step must go to scale up these systems to bigger facilities. Well,
I have the impression if we really scale up electrolyzers, and we need a lot of platinum in these electrolyzers, these PEM electrolyzers, also the price for platinum will go up, will rise, because the demand will get higher. Absolutely. So that's going to be a problem. Could you imagine an PEM electrolyzer without platinum?
Completely without, probably it'd be a little bit difficult. But with reduced platinum or platinum material, this is possible. At the moment, normally you are in the range of more than 1 milligram per square centimeter, and you want to reach down to, say, 0.0 milligram per square centimeter. But this is only one possibility to reduce the cost. Another thing is, for example, when you are using the bipolar plates of PEM electrolyzers, they are normally made of titanium, because they have to work in a acid atmosphere.
Which is not cheap.
Titanium, titanium is not cheap, and if you need it in big amount, the price will increase strongly. And for this reason, we are trying to replace these titanium bipolar plates by probably stainless steel plates. But stainless steel is not stable in acid environment, so you need additional coatings to shield it for corrosion. And this is one thing we just started to do some months ago with so-called plasma spraying technology, to put a thin titanium layer on top of the stainless steel plates, and so the price could reduce and the stability is the same like with a massive titanium bipolar plate.
Dr. Arnold, is that you're doing research on both sides, PEM and SOE, but what is your personal opinion? Which one will win the race?
If I would know this today, I would be a rich man.
You would bet on it, eh?
I would bet on it. I would be a rich man. The chances for both are very high, I think. For sure, the SOE, if it is successful, has probably some more. The probability or the likeliness that it will be more successful is higher, but we can't say today. You have to confess, the PEM electrolysis is much better developed at the moment than SOE. SOE is just started. PEM electrolyzer is now running for 10, 15 years already. So this is the difference at the moment.
Or maybe alkaline will show up that it can be better and better and win the race. There you have to do some better coating, I think, huh?
Yeah. What I told at the beginning, these coatings we developed in this high solar project, they worked very good and we tested it for a long time, but it was not the optimized solution. There is still some possibilities to do there. So to say the cathode coating we had at that time was very successful, and I guess the potential of development is not so high. But on the anode side, the coatings have a high potential for future developments, and I think this is what we are really trying to realize in the next few years.
When I tried to explain SOE, I said it's a reverse SOFC. It's like the fuel cell does the reverse thing of an electrolyzer. Will we one day maybe see a fuel cell that's on the same time also an electrolyzer for, let's say, application in a car? You know, if I have in a car a fuel cell that can produce the hydrogen itself just by plugging some electricity in it, would be wonderful, wouldn't it?
For sure. We call it a bifunctional mode of a SOFC or SOEC. And if we are able to get this would be really great. The question is this kind of combination in one system of an electrolyzer and a fuel cell really the maximum or the maximum efficiency you can get out of such a system? Or is it possible to produce two independent systems, a fuel cell and an electrolyzer, who are much more optimized and are much more efficient? This has to be shown. For sure, if you can put it in one system, it would be smaller and the design would be more easy to handle. But we will see what is the result.
Dr. Arnold, I'm here with this group exhibit since 20 years, and I was a lot of times thinking, well, we are very close to the breakthrough, and now I have the impression again. But what else has to be done that we really have a big breakthrough for this technology?
For sure, in the first time, we have to be technologically and scientifically successful. This is quite clear. But there's on the other hand, I guess one thing is very important, that we have to convince our people, that we convince the German population. Because if you have in the end a very good, successful technology, but nobody wants to take it, what have you won? Nothing. And therefore I think in parallel to this technological and scientific development, we also have to do some more explanation to politicians, to the public, and then we will see how it's going on. But I think it's very important.
That's exactly the reason why we do these interviews here on stage, and no technical presentations, but interviews face to face. And I hope people can understand what we are talking about here and understand a little bit more about technology. Who wants to go into details can just go to the booth of Deutsches Zentrum für Luft und Raumfahrt, just opposite there, C66, and visit the gentlemen and ladies over there, and can talk to Dr. Arnold also after this presentation. I would like to thank you very much for this interesting talk to you, Dr. Arnold, and I like you very much and would like to thank you very much for your attention. Thank you very much.
Thank you very much.